and then get 6 and divide. And 6 over 8 equals x, and then you can reduce that to 3/4. And then you can plug 3/4 in for x and see if it's the equivalent. And that's a review from Friday. There's actually another topic we talked about Friday called the change of base formula. This is the last call if you want to turn it in on paper. All right, the change of base formula was on page 598. So if you want to open your books to 598. I want to review it because it's like a small step in today's work. So it's important that you understand and remember the change of base formula. Okay. So, like for instance, number 30 was assigned to you. It was log base 5 of 13. Right now, this logarithm is base 5. You can change the base if you set it up into a fraction correctly. The 13 goes up high in the numerator, the 5 goes in the denominator, and your new base is base 10. This is useful because most calculators do base 10. So then you can hit the fraction button on the calculator, log 13 divided by log 5, and you get your answer. And then you can always check it. 5 to this power is 13. So who wants to ask a question about change of base formula? Especially if you weren't here Friday. Alright, then the other assignment was 6.6, 1 through 8, chapter, or page 609. Here was number 8. This was the very last problem in your assignment. The answer was 1/2. I have to do it when I find out. People figure that out. And the Friday after. Oh, that's what it's for everyone. So I that's so much, right? We have like a week. All right, so I don't know. No, that's 6. Yeah, because I did 6.6. What number? That's what you do, right? What's this? Wait a minute. So I missed like the deadline for the match. Mariah. All right, who wants to ask a question about 1 through 8 besides number 8? I left this one up here. All right, then, should we look at the third level of difficulty? Alright, I got some steps here. So this is what happens if you need to solve an exponential equation, but you cannot make the same base. So look at, we have a 7 and a 15. These numbers are unrelated. They can't be rewritten similarly. So we don't have all this option. It is kind of a long process. So it's up to you if you want to write the steps or if you just want to show the work. Honestly, just doing the problem, you might remember the steps. Alright, so the first thing you want to do is isolate the base. Now on this one, the base is already isolated. But they do get more complicated. We'll see a more complicated one right after this one. But if there was like a plus or a minus here, we would want to move it around so that this base 7 is alone. After that, if you cannot make the same base, you're going to write the log on both sides. You'll use a logarithm. You want to use a logarithm that will match the base of the exponent. So we'll use log 7 this time. Log 7 of 7 to the 9x equals log 7 of 15. So that's your first time ever doing that. You're taking the log on both sides of an equal sign. This on purpose matches this number. If this was a big 8, we'd have a little 8. If this was a big 20, we'd have a little 20. Now we'll do the power property, which I don't, after a while we stopped showing this stuff in our work, but to make it make sense at first, let's go ahead and we'll move the 9x to the front like we practiced last week. And then it's 9x times log base 7 of 7 equals log base 7 of 15. Last week I had some log facts over here on the board. And one of them was if the base matches the argument, that logarithm equals 1. Because in that case, you're saying, like, well, what power of 7 equals 7 is 1. So anytime the base matches the argument, it cancels to be 1. So since we did the log on both sides, this now is canceling to be 1. That's a 1. So we got 9x times 1 equals log base 7 of 15. And then 9x times 1 is just 9x. And so now I'll use that change of base formula we just discussed. Oh, there's an answer down there. So that would be, okay, 9x equals log 15 over log 7, change of base, step 4. And then I would divide by 9. Now I don't like to divide a fraction, so I'm dividing 9 here, and I'm just going to do like an old school division sign there. And so now x is going to be log 15 over log 7. I'll use my fraction button, and then I'll divide by 9. And that'll be the answer.
Can I take a picture of that?
So you gotta like try it. See if you can even enter that in. Correction button, hit the log button twice. 15. Log button twice. 7. Divided by 9.
How close are we supposed to get the number? Like, how many decimal places?
3 decimal places.
What's zero?
Inquiry.
Wait, how'd you get there?
That's good.
We got 0.0.
We're wanting 0. That's a good thing. You may have a mistake there.
Oh, never mind. Actually.
I'm just kidding.
Now you can check this. So if I feel like I don't know if I did it right, I'm just gonna go to the original problem and I'm gonna do 7 exponent 9 times 0.155 and it should equal 15. And if you still have the full decimal stored in your calculator, highlighting the full decimal is even better. It'll come out like 15.0000008 if you pull in the full decimal.
Right now.
3.
And the first number is 0.
What number are you talking about?
Number 9.
Maybe it's 0. Have you tried 0?
Yeah, she's already answered.
So you think it's 12? Maybe it's 12. 11.999. I was very 12. All right, we are now going to look at one with base E. And base E might be the most important base because it's describing our natural world. So I want to remind you that log base E is the same thing as ln. And we're going to look at a law made by Newton. You guys know who Isaac Newton is? What did Newton do? Yeah, he's the one that talked about the apple falling, this is gravity, laws of motion, things like that. Well, this was a big one for him that's used still a lot today. Newton's law of cooling is a exponential equation. So go to page 604. I'm going to give you this formula on the test, but you have to be able to plug in and solve it. So you don't have to memorize it.
So you can get it.
Yeah, it'll say use Newton's law of cooling and find how long it takes for something to cool off. So an important application of exponential equations is Newton's law of cooling. This law states that for cooling substance with initial temperature T sub 0, it's pretty blurry up here. I'm going to try to read it. But you guys may have heard of this. I think it happened before you were born, but someone sued McDonald's for their coffee burning them.
But they have a couple now.
Yeah, they got millions. And at first, we all made fun of them. Like, you spill coffee on yourself and you're suing McDonald's. Like, get a life. But then it came out that actually there were like coffee makers that they were producing and using were making like crazy hot liquids. So they were handing over liquids that was like blistering and scalding people. So that coffee maker was really unsafe for use. So that's why they won it. So there is a conversation to be had about, especially with like air fryers and things, like how hot we can make food. You have to make food really hot to kill bacteria. And then how long does it take to cool before you can actually serve it? But this applies also to like engines overheating, to like cell phones getting too hot, these laws of cooling. Okay, so go ahead and label so you know where to plug in each thing. The regular T is your goal temp. T sub 0 is the initial temperature of the item. T sub R is the surrounding temperature, so that's the room temperature. E. Why is E a part of this? Well, in nature, something consistently cools. It doesn't just cool for a little bit and then stop, and then cool for a little bit and then stop. This is continuous decay. You got your rate, your cooling rate up here for this liquid. The cooling rate is 4.6% every minute, continuously cooling. The little t is the time that we're solving for, and again, T sub r is the room temperature. So this one is about a stew. It says alicha. Some people have had this. It's an Ethiopian stew. When you take it off the stove, it's 212 degrees. Is that appropriate? How hot does chicken have to get for human consumption? 165. 160, 165. If it doesn't get that hot, there's bacteria in it. When you consume it, it grows in your stomach. You get very sick. You can die from salmonella, but that's why when you warm up your nuggets or your meatballs or whatever it is, it has to get to 165 to kill off that bacteria. So this is 212. That's reasonable, but you don't want to eat it at 212. It says the room temperature is 70. I know kitchens can get really hot in a restaurant. The cooling rate. How long will it take till the serving temperature of 100? Are we really serving soup at 100 degrees? What's the temperature of your mouth? Yeah. What's your body temperature? 96. It's 98. 98.9. Generally. Varies a little bit. So if you consume something lower than 98, it's not going to feel warm. So we're looking at if we want something to be hot, you want a hot tea, a hot coffee, a hot soup, it needs to be, over 98. So 100 degrees is a reasonable serving temperature. This is a reasonable cooking temperature to kill bacteria, and then it has to cool to a serving temperature that won't burn the mouth. We looked it up in one of our classes. It was like 110 degrees, and you're going to start getting blisters in your mouth. So when you pull your French fries out of the air fryer, if it's way too hot, it's probably like 110. You guys should get your thermometers and start measuring it. Okay, so let's look at the order of operations, how this Newton's law of cooling works. Okay, here's the initial temp of 212, the room temp, the cooling rate. This was our goal temp to serve at 100. First, subtracting 70. Then 212 minus 70 is 142. Jolie, what'd they do next? Yeah. Okay, well, first they divided by 142, but yes, then we have base E. So they did log E of both sides. And log E is the same thing as ln. And so ln E and log E cancel each other out. It's like E to what power is E? Lastly, dividing by negative 0.046, then it's about 34 minutes. You should wait 34 minutes before serving this stew. I don't think it is like if it's in a kitchen with stew, but like they're not making coffee 34 minutes before they serve it. They're making it like a minute before. So whoever manufactures that coffee maker at Starbucks or McDonald's, how hot is that coffee? And if they made it hotter, like could they make it more quickly or could they store it longer? Things like that. Was it an engineer that made the coffee maker that's in every single McDonald's? It was. Okay. All right, let's try it. What'd you say, Connor? What did it say? 81 degrees?
No, I searched up food temperatures.
Yeah, I'm curious.
It said between 41 and 35 degrees Fahrenheit.
Right.
That's in the danger.
Yeah, we live.
41.
No, like ice cream's frozen. Once your ice is like 31 degrees, you're gonna start like risking frostbite. Like if it's prolonged in there in your mouth. All right, let's try it. So let's say it's the exact same scenario with Stu, but our room temperature is 75 instead of 70. If it's warmer in the room, it's going to take longer for it to cool. So let's see that relationship come to play. All right, so it's the temperature is, what is it? Our rates to our rate is 4.6% every minute plus our initial room temperature of 75. All right, so we want our stew to be 100. That's how we can serve it. It's starting at 212. That's what made all the flavors go together. They got 5, 4, 6. Just like the example. And then 75. We don't know little t. That's actually what we're trying to figure out. How long would it take to cool correctly? All right, let's isolate. So step one, oh, I forgot the base E, the most important part. So we need to isolate base E, so let's subtract 75 first. And then I believe that's 137. 212 minus 75.
Yes.
137.
Yeah.
Times E, because it's continuous decay. Continuous cooling. And then divide by 137 to get E alone. And I'm not going to actually divide that. I'm going to leave that as a fraction so I don't have to round early. Okay, I'm very close to figuring out little t. Can't make the same base, so I'm going to do log base E on both sides. And log base E is the same as natural log. So you can pick how you want to write it. Do you want to write log E on both sides or natural log on both sides? ln. No, log E of E, whenever the subscript matches the argument, it cancels. And this is the same as ln. I just don't have enough room. I bet you don't either. Okay. So my answer is going to be, I'm going to go ahead to log. Natural log 25 over 137 is negative 0.046 times T. So now I will divide by the cooling rate. And now I'm ready for my calculator. In my calculator, natural log fraction 25 over 137. I'm going to go ahead and close parentheses, divide by the cooling rate, and that'll tell me how long it takes.
G. 14.2.
It should be 37. Yeah. Yeah. Should say 37. So in a room of 70 degrees, it only takes 34 minutes. In a room of 75 degrees, it takes 37 minutes for the stew to cool from 212 to 100. So I'm interested if anybody in restaurants like has cooling timers. I'll come look at it in a minute. All right, so your assignment Page 609, 1 through 8. That's it? No. Yeah, it was so 3 to 4 word problems and all that. There's a lot of applications with the students now. Well, I don't know. I forget some of the and get the things. Calculator up, I'll look at it.